So now I'm finally ready to apply the moment area theorems. And the first one I'm going to calculate is this vertical distance to point B from the tangent line at A, which says that TBA is equal to this first moment of area of the integral, or this AB m over EI times dx. And this integral, this AB part right here, this from A to B, this integral represents the area from A to B of the curvature diagram. And this x bar represents the distance from the centroid of this area, which I will put in red, to point B. So this distance right here. And we know from before the length of segment AB was this lowercase a, so the centroid of this triangle is a distance 1/3 a, or a over 3. And so when I try to solve this out here, let me put a little subscript b there so that you know that's the distance from the centroid of the area to point B. This, if I go ahead and I plug and chug right here, this will be a over 3 times the area in purple, and that area in purple is just 1/2 the base, which was A, times the height, which is negative PB over EI. And just work out some little algebra here. This will give you negative 1/6 PBA squared over EI. The negative just means that the point B is below the tangent line at A. Right here, if I look over here, you see that point B is below the tangent line at A. So here's the tangent line at A, here's point B is below it. So now that I have TBA, I can calculate this angle phi. And you know, I'm only worried about magnitude, so I don't need to worry about the negative sign out in front here. So this phi is equal to PBA squared over 6EI divided by A, which is just PBA over 6EI. So there's that angle, and now I can just go through and proceed with all this other stuff. I can even calculate D, right? This distance D, this vertical distance D, and this D was equal to A plus B times phi, which was PBA over 6EI. And now I just need to apply my moment area theorem one more time and calculate what this TCA is, or the vertical distance to point C from the tangent line at A. So let me bust that right here. And if I write out TCA, looking again at this moment diagram, I know that this TCA is, you know, this is the formal theorem, A to C m over EI times dx. It's the area of the curvature diagram all the way from point A to point C, which I'm allowed to break up into segments. I kind of replace the second moment area theorem sometimes with this summation, just like when we calculated centroids. And here, you know, with this x bar I, AI kind of business. That the reason I can do that is because I can break this up into two areas. The second area being this area right here, and I can just sum up the first moments of area of each of these to point C. That distance is B, and the distance from the centroid of this orange region right here to point C is 2/3 B. So now I just got to work this summation, or this first moment of area calculation, using the two geometries here, or this summation. And so I know for, let's call this purple area the first area. The area of that is 1/2 negative PBA over EI. And the distance from point C to the centroid of that is actually this total distance right here. And that is B plus A over 3. Plus the orange area, which is 1/2 the base, which was B, times the height, which is negative PB over EI, times the arm, which is 2/3 times B. And what we will get after we work out this algebra here is, I'll get this TCA is this negative 1/2 PB squared times A over EI minus 1/6 PBA squared over EI minus 1/3 PB cubed over EI. And you'll see that if you look at this, all this has units of displacement in it, because EI is a force times distance squared. And now I can calculate based on this last part. Now I can apply this last portion right here and calculate the magnitude of the deflection at point C. And again, I can remove the negatives because I'm only playing with magnitudes here. This delta C, the magnitude is equal to TCA minus D, which is essentially this mess, which is this mess right here, with an absolute value, so everything becoming positive. So let me rewrite that. So here this will be, so that mess right there minus this D over here, PBA squared over 6EI minus PB squared A over 6EI. And I'll know right off the bat that this one cancels with that one, so that's nice. And if I combine everything together here, I will get that this delta C is equal to 1/3 PB squared A over EI plus PB cubed over 3EI. And that is the magnitude of deflection at point C. Now it's important to remember this is the magnitude of displacement at point C, so it just gives us the distance or the magnitude. It doesn't indicate whether it went up or down. We know it went down, so if we had an actual coordinate system here that where we said this is plus x and this is v for vertical deflection, and any displacement above the x-axis would be positive, anything below it. So in this case, the displacement at point C would actually be negative the magnitude of delta C. Okay, so that would actually be my answer if you had to give an orientation associated with your number. Alright, so maybe this problem would have been easier with numbers, but hey, don't judge me, judge yourself. What's up? Let me know if you have any questions. See ya.